what we've done here is this is basically a tribute to Toma Beardena and his life's work and my life's work in electromagnetics. So everybody always asked, is it possible to get the energy, from a different time domain, which Tom talks about.
Okay, John, this is, wow, it's enormous.
Yeah.
What are you going to talk about today?
One of the biggest monopoles we've ever built.
Yeah.
With,
how big is it?
it's 12 feet high. It's 12 feet. So,
The diameter?
yeah, it's 12 feet in diameter, and the wheel weighs close to 300 pounds.
Wow.
With this added weight on both sides, probably 450, because the magnets are very heavy. This is a steel-backed plate.
What is this in the middle?
That is a self-regaging, idling magneto, which means that if it goes above the speed that it's rotating at right now, it generates to put power back to help recharge. But then you have this coil, the master, and two slaves on both sides.
Okay.
And all these coils, I want everybody to understand that everything is paralleled in this system. All three coils are in parallel, which means they're all hooked together. Now, what you're actually watching here as it runs around here is this piece of equipment right here has to supply 42 pounds of torque to turn the wheel.
Okay.
And it's supplying that by regaging these star magnets that are by, see the dots?
Yes. Yes, I do.
Each time the dot comes across on timing dot number 1 here, see?
Yes.
Each time the dots come around
Yeah.
and these dots line up, see, it fires 5 times for 10 poles.
Okay, so every other pole.
Yeah, so every other pole, but there's a reason for that. Each time these dots line up, there's a little regaging impulse here.
Yes,
See?
I see it. Yes.
And that little impulse, the first flash, is the little bitty spike
That Tom talks about.
that Tom talks about to change the magnetic fields, the motor magnetic fields, right? So we can look at it as motor, as an electrical motor,
Yes.
but not quite, because as it does that, it develops that little spike, switches these permanent magnets that are on the back. In other words, it flips their direction. And by doing that, it self-powers itself around the wheel. So it flips the magnetic field, it gets the little bitty spike, it gets an impulse. Can you see it shake just a little bit every time that it fires on that impulse? Watch. Look very closely.
What shakes? The dots? Those things, okay.
The magnets shake, see them? That's that little bitty spike trying to flipping the magnetic field. See it shaking?
Yes, just,
It's
very
vibrating,
slightly.
right. So what happens is there's a metal back here and there's a metal back right here. And it fires this and makes a U-shaped current, a U-shaped magnetic field that gets shorted out against the next magnetic field.
Okay.
So when it fires that and the magnets flip direction, they automatically get sucked in to this next pole with zero current. There's no
Okay,
current.
so it hits that dot there and it fires, and then by the time
Well,
it reaches
see it here?
this pole here,
Come over here. And see this dot? When this dot meets this dot,
Yep.
see, it fires, and that's when it shakes.
Yeah.
So that little bitty spike that Tom Beardena talks about that's this big, right,
Yeah.
reverses the fields in the magnets, actually reverse them. These are barium ferrite magnets. They've been here since 1984.
Okay.
They were cut for me by AZ Magnets in 1984. So remember the work that's on Tom Bearden's website
Yeah.
about Radis, about the regauging magnetic shoes.
Right.
Well, the reason that all that material is limited is because you could make a self-rotating permanent magnet motor that didn't burn any energy. And that's what you're watching right here with 44 foot-pounds of torque.
Okay.
Okay? So, every time, you can see it here, the bright blue is the regauge. That's energy coming back for nothing. The first blink,
Yeah, I see it.
Is
Just a
the-
quick blink and then it's...
the quick
it's-
blink
it
is the
holds
little
it for a
spike
while.
that
Yeah.
flips the magnetic field.
Right.
Okay?
Right.
And that's accomplished. It's real sharp. It's a trigger circuit. Inside, there's a disc with 5 magnets on it. And then there's a Hall effect device. And this is a switch inside here that Ron Cole and I developed called the Bedini Cole switch. That's used on all the window motors. That's used on some of the monopoles. It's being used on this monopole because of its enormous amounts of power modified. So, what's happening here, Pat, is here's the little bitty, here's the current meter, because the big motor, this motor is not running
Yeah.
right now. What's turning this wheel is that permanent magnet when it flips poles.
Yeah.
And so what you're seeing here is you're seeing no current here, 0.
Right.
And you're seeing no current in the recovery whatsoever.
So these batteries are completely standard?
Except, watch,
Ah, okay.
when we turn, now earlier, I took, these are 36 volt batteries. That's 3 12 volt batteries in series for 36 volts. There's a Fadot current that Tom talks about, a delta Fadot current, which is a 0 current, which is a current that's not fully understood by all the engineers.
Yeah.
They don't deal with this because, see, here's the problem. You're an electrical engineer, I'm a physicist, and the next person's a doctor. Do we talk to each other? No,
Not if we can help it, right?
but we don't.
Yeah.
So electrical engineering does not talk to physics,
Yeah.
and the physicists do not talk to the electrical engineers, unless they're golf buddies and they're out on a golf field somewhere. So it's very, what you have to do to deal with all this is you have to have a real open mind, and you have to sort of be a jack of all trades, and you have to keep focused on these particular little fields that deal with this type of electromagnetics, which is scalar electromagnetics, or what Tom likes to talk about, energy from the vacuum. So since he's 80 years old, and it's his birthday, happy birthday, Tom,
Yeah.
because here's the machine
That he's been talking about.
that he's been talking about for years. And so it's basically a tribute to Tom and all his hard work.
Yeah.
I'm sorry if most engineers get his book and go, this is hogwash, because it's not.
Yeah.
If you understand exactly what these fields are that are circulating right now, you can drive this 300-pound wheel continuously at this amount of RPMs for no power being drained from the batteries. Mm-hmm. Okay, so basically what do we have, Pat? We have a motor that's using the same thing as we talked about in our early DVDs, which is, it's like a nerve firing. So the nerve fires, it jumps the gap, and then it's translated into electromagnetic energy and your arm moves. So we fire a little bitty spike from the control unit in here,
Yeah.
which you can see right here again. I'm going to point it out again. This little flash first.
It's like a double flash.
Yeah, it's very quick.
Yeah.
It's very quick, and
Yeah.
it's a set of instructions
Okay.
to tell the permanent magnet fields what to do, to push back. So what we want to have happen, if this is what was a North Pole, we want that to flip to a South Pole, so we have to give that magnet a set of instructions to do it. Mm-hmm. And the spike, this little flash with the little timing wheel up there, is a set of instructions when this little pie-shaped magnet comes across the
Yeah.
pole.
So that looks about the same size as the magnets that are on there.
That's right.
Okay.
So the magnets are barium ferrite magnets, and you can see that because they got a rust color on them. See them? Mm-hmm. They're red. So, see how they're...
Yeah.
Okay, so what we had to do was on some of them, since we only had half-inch cuts, we had to make 1-inch thick magnets. So these are the oddball 2 magnets that we left out of the wheel
All right.
because they don't quite
They're
fit.
not quite the
And
same
we had,
size, yeah.
yeah, we had just enough to do this, and you can see these are solid.
Yeah.
And then you'll see one come around that's split right there.
Right there, yeah.
Yeah. So there's 2 sets of split magnets that are bonded together.
And that's the only one in here that's split?
Right. Now,
Yeah. Right there.
in everything that I do, Pat, and I do with Toma Beardena, I pretty much make public. So if you look very carefully, you can see that these magnets, there's a piece of aluminum along each side of the magnet that's screwed in there.
Yeah.
Okay,
Yeah, I do see that.
this is going to rotate. So the magnet is inset into the wheel. Don't think it doesn't have a strong field, it does.
Yeah.
The field's all the way out here, so it's kind of hard to hold it. But
Yeah.
they're inset in the wheel just like this. And so these pie shapes are rotating around, and there's a reason for the shape. Mm-hmm. Because we want the magnetic field to regauge this much larger at the back than we want at the front. And so what we do is we come in with that sharp pulse, if you look right there, that this goes through the center of the magnet.
Okay.
Okay? Now, you're probably asking yourself, these are also magnets.
Mm-hmm. Yeah, the bottoms. And they're all at an
All right?
angle.
Right. But anyway, let me just finish with this,
Okay.
and we'll jump right down here to this.
Okay.
What happens is that little impulse, this little blue light, when you see the first spike, and then you see a steady blue pulse.
Right.
The magnet generates its own energy when it flips its own poles. So that's the long part of it.
Yeah, so it's like a double
Right.
fraction of a second,
And-
like almost a second.
And the thing that's very important here is what you're actually looking at here is probably one of the most nonlinear fields that's being brought together. It's nonlinear in the beginning, and then it goes linear when it flips.
Okay.
All right? Which means it has a motor force after that. And that's what you see driving this wheel around. You notice it's a constant RPM.
Yeah. So you were saying about the flashing.
Okay, the little blue light, this is the little initial firing, a little bitty spike, right? It's not a pulse of energy. It's more like this thin, where a pulse of energy might be like that.
Oh, I see.
All right? So we've changed it to just be this width. So it's a spike.
Okay.
In that spike, when you first see this spike appear, you see this double little spike. And then all of a sudden you see the blue glow and
Right.
stay glowing.
Right.
That's at the point that you can see the wheel shake when
Yeah.
it's on the dot.
Okay.
And why it does that is the magnets, these magnets are north in this direction, and they're south in the other direction.
So north on this side
So,
and south on this
so
side?
we're stationary, aren't we, Pat?
Oh, okay.
In the wheel.
Yeah.
So we come by, we hit the barium ferrite magnet with these poles in this arrangement.
Right.
And we hit this barium ferrite magnet, and what we want to cause it to do is send a little signal in here and make the magnetic material inside flip poles.
Okay.
So it does it really quick. And that's the shaking you see, because it wants to turn around on there and it can't turn. So it just shakes.
Okay, yeah.
All right? So you understand that now?
Yeah.
And so the next thing that happens is it gets the impulse here, right? Gets that little impulse and it shakes, see it? But when it turns itself around, it's attractive because this is still energized, and that's the energy that's coming from the flip and the magnet, the long blue pulse.
Okay, yeah.
That's the motor itself. That's the force that's pushing this wheel. All right?
All right.
So if we stop, if we slow it down, I don't want to get my arm in there. I had my arm in there before. To where it has to really work. Now, here's the problem. Here's the engineering problem. If we just tell the motor to slow down, right? Let it come across the pole. These are magnetic locks in this condition.
Yeah.
In other words, they're being attracted into the iron down here.
Okay.
This iron pole right through here. See?
Yeah.
And so what you're watching now is when it hits that little spike, see it shake? Watch. It's when the magnet flips around.
Okay.
You can see it shake. It can't flip over on the board. You follow me?
Right, right.
So watch it real close and it'll shake.
It doesn't seem to shake right there, though. It seems to shake just past it.
Yes, it does, because it stores that and then flips.
Okay, okay, yeah.
All right? So that's why you see that happening. Now, here's the problem. You have this big lever that's 6 feet, right? So the force out here can be very little, and the torque in here can be very great, because it's a lever, right?
Right.
I've got 2,000 pounds here, and I've got an ant lifting the 2,000 pounds.
Yeah,
Well, that's easy for this wheel.
yeah.
See, this way. But now what about this lever?
Uh-huh. Yeah.
It goes directly to the shaft. right? And this lever has to, it's a lever like this.
Yeah, it's very short. Yeah.
Yeah, so it has to be enormous in torque to lift that direction.
Yeah.
See?
Yeah, I can see that.
Okay. So the only way to do that is to re-gauge and get the energy out of the magnet.
So that's why you designed it like that.
Yes.
Yeah.
And also that when I start the motor, what'll happen is this is the motor force at this speed. So anything over this speed, this motor will be off and become a generator.
Okay.
You understand? Because it has the north and south poles all the way around, and it has 10 poles. And it has, I don't want to leave this out for everybody, each one of these coils has 2,206 turns
What do you
of
mean by
number
turns?
18 wire on
Turn
it.
it that way? This way,
No,
or
no,
this
that's
way?
how many turns of magnet wire on each coil.
You're just
Yeah, you
going
turn
around
them on a
the,
bobbin, right.
Perimeter.
Right.
Yeah, okay.
And so they're in series,
All right.
and when it's in this condition, 5 of them, it can only fire 5 little spikes as it turns around, and each one of those little spikes, right,
Okay.
is firing there and the dot.
So what happens to the other one each time?
It just,
Just passively?
no, it becomes the opposite pole, and when the magnet flips, it attracts it in.
Okay.
See?
Okay.
All right, so next thing is the switches. What the switches do. When this switch is up, it is reading. Do you want to read that? What's it say there?
It's at the top of the green. I can't see what it says.
Yeah, but it's in the charge, right?
Yeah. Yeah.
So it's
charged.
above the green.
Yeah.
That's a 36 volt current meter. In other words, it requires real power to keep it there. It's not a digital meter. It's not one of these.
Okay.
It's an analog meter.
Yeah.
So that means that you have to supply power. So it loads a battery to read it.
So right now this is charging these batteries.
Right now, no. It's telling you that the primary batteries are above 36 volts.
Oh, okay.
And they're in the green. So this is telling us that the primary batteries are ready for operation to run the machine,
Okay.
because they're not really supplying what they could supply.
So were they
Here.
running the machine before? No.
No.
Okay.
All right. So when I push the switch downward, I'm looking at the recovery battery. Now remember
So
earlier,
it's a 3-position switch.
yes,
Okay.
yes, 0 off in the center, because you don't want to burn the energy keeping that meter on, because it will.
Okay.
Probably a little bit more than your car radio takes.
Okay.
This is showing you the recovery battery. Now here's the important thing. If you flip the switch yourself,
Yeah.
John doesn't want to touch it.
You want me to switch it?
Well, I want you to read the meter and tell me which one's higher, the bottom position or the top position.
Right now I think it's the bottom position, but let's see. Yeah, the bottom position is higher.
Why is that?
This one's getting more?
Because when this, see, everything returns out of here through these wires. We just put them in the frame so they wouldn't just be all over the place, because we don't get them tangled in the wheel, but they're right here, see?
Right, I saw that, yeah.
Yeah.
Yeah,
So,
they're just in the guts here.
so, remember Tom Beardena talked about the 0 Fadoc current, the current that surrounds the wire.
How do you spell Fadoc?
It's just 0 phi, excuse me,
Oh, okay.
phi, all right,
Okay.
or delta phi. I think that's what it is. Anyway, there's too many of those formulas.
Yeah.
So that current has no mass to it. It's massless. And
Alright.
that's what's flowing right now in the whole system and being collected here. Because if we turn this meter on, that meter says that there's 38.1 volts in that capacitor. There's 36 volts here,
So this is 2 volts over the,
of course.
yeah.
So it's just maintaining that with no current. So it's a current that's massless. That's what he's talking about. So what do you do with a massless current, right? Well, a massless current can do a motor function with enormous amounts of power because it's drawing its energy out of space, out of time. That's why Tom says that it's a time charge. So all you have to do is trigger the active vacuum correctly and you'll get this motor function.
Yeah.
All right, so now we're going to move on to triggering a little bit more out. So the first thing that I actually want to explain to everybody is this coil is the master.
Yeah.
And this master coil has about 150 to 200 pounds of wire on it.
Wow.
And that's quite a bit of wire because each one of these spools weighs 80 pounds. It has a 3-inch core. It's made of welding rod. You can see it here. And the reason that we use this welding rod is because each rod is copper coated and each rod is more or less insulated to break up the current in the coil, the eddy currents,
Okay.
so that we don't get a big heating effect. So everybody that built a monopole motor that used just an iron bolt is making a big mistake. And you see that all over the internet.
Yeah.
You see people
won't go that far, they won't.
just take a bolt
And grind it
because they're too lazy to cut the welding rod or find the material to build the machine right.
down. Right.
So when they fail,
Yeah.
they only fail because of their own laziness in building the system.
Or they're only
So-
incomprehension of the
Right,
thing first.
so
Yeah.
something very special here is this coil
Yeah.
and the 2 slaves. Because all 3 of them are identically going to do the same thing. All right? What's going to happen when we start this motor is there's a timing mechanism on the other side over there.
Okay.
And each one of those magnets on the wheel on the other side corresponds to each magnet on this wheel.
All right.
All right, now you're saying to yourself, John, why?
Yeah. Do the magnets actually talk to each other at that distance?
Yeah,
Yeah.
because if you took a line of magnets, it's very simple. Sometimes it's hard to see, sometimes it's simple to see. If you take the 2 magnets, right? This is like dominoes. So if they're all spaced evenly, you move one, the other one moves. The other one wants to move, see?
Oh, so they're pushing each other apart right now. Yeah.
Well, this is a monopole. Remember, it's a monopole. So all north poles facing out, right?
Okay.
The magnet you see in the back at that angle shapes the magnetic field because the magnetic field wants to come around the magnet, you know, like this,
Okay. Yeah.
like 2 circles on the side, right? So what we want to do is we want to pull the North Pole in very quickly towards this neomagnet that's on the top. Now, Howard Johnson did that for a simple reason. Is because when you put two different materials together in the magnet, you cause a switch to take place in the magnet, in the field.
Mm-hmm.
They don't teach you that in physics. You're not going to learn that in electromagnetism or with those kind of materials. I'm sure somebody knows,
Mm-hmm.
but the world doesn't.
Yeah.
All right. So what we have is a permanent magnet field right here. And we have an electromagnet here, an electromagnet here. And what the whole purpose of this machine is to run on a sort of scalar potential. Because these magnets aren't very big in proportionate to the wheel.
Right.
They're not real big, right?
But they seem very big in proportion to the timing ones on the other side.
Yeah, but the timing ones are much more, right. But the magnets in this wheel overpower the magnets in this wheel.
Okay.
And you'll notice that these magnets are in between the spokes for 10 of them.
Yeah. Yeah.
All right? What's going to take place here is what we want to do is everything that the machine's doing work-wise, supplying energy,
Mm-hmm.
we want to recover every bit of energy and more. So we want to go above their level. We want to go past 100%. So how do we accomplish that, right? By shaping the fields. And that's what
Oh,
these
okay.
metal plates are here. This is actually shaping the magnetic field to make it into a little bit wider flame
So how do you know the angle to put those
by
up?
tuning the machine, by watching the speed of the machine.
Oh, okay. So it's all trial and error.
Well, it's a knack for
Yeah.
tuning the machine.
Right.
Not everybody's going to be able to do this,
Yeah.
and not everybody's going to be able to understand
Yeah.
what the machine, how the machine
Yeah. but
functions.
What I meant was you don't go to a book and say, okay, if it's this big and you need this angle. Or...
There is no book on this,
Right.
Pat.
Yeah.
You know, and if anybody wrote the book, it's Tom Beardena.
Yeah.
So
Okay.
there's your credit again.
Mm-hmm.
So here's a man that meticulously searched night after night, night after night, night after night, through all kinds of reference material, and picked out one little bitty thing
Mm-hmm.
that's hidden in some book somewhere.
Yeah.
And he wrote about it. I mean, there's thousands of pages
Yeah, I know.
on Tom Beardena. And you read this stuff and you sort of scratch your head and you go, no electrical engineer will read it.
Mm-hmm.
Some physicists will read it and go, well, maybe the guy has an idea. But if I work on that, I'm not going to get any funding.
Yeah.
So Tom, all these years, has probably done it without very much funding, like everybody else.
Yeah.
Because you can't get anybody to invest in anything that's going to do this. So, what we want to create is 3 magic windows. 3. We want, these windows are open right now, so everything surrounding us is all in different vectors. This way, that way, this way, this way, that way, right? It's already there. What we want to do is cause a compression cycle. So, when we flip this switch on, we want 3 compression cycles.
Okay.
We want 3 compression cycles that are going to bump 3 magnetic fields all at the same time. Magnetic field 1, 2, and 3.
Okay.
Because they're gonna want to spread out. We want, as this one is collapsing and flipping, to bump this field that's going the other direction.
Okay.
And this one to bump the other direction,
Okay.
even though we're kicking out. See, there's a spacing geometry here. You notice that this coil is in further on the wheel, and this one's further out. If you look,
What do you mean it's in for?
it's in
Oh,
further.
this one's closer to center than this one?
Yeah.
Yeah, yeah, it is. Huh.
Yeah, because we want to bump 3 stages.
Right.
You follow me?
Yeah, I see that now. That one's, yeah, it's much further
Yeah.
that way, yeah.
Yeah, and we want to shape the center one to make it just go in the shape from the pole. It's going to bump this magnet, see, which has another magnetic field. So what we want to do is we want to cause this nonlinear action, because what we want to do is we want to capture everything that surrounds the coil, fill the capacitor,
Yeah.
and dump it to these batteries. And so what we want to dump, Pat, is about 14 joules times 3.
It's 42 joules.
Right.
Yeah.
Times 60 seconds, times 60
All right,
minutes.
All right, too much.
Yeah. All right. So when we fire the machine, we're going to bump it.
Mm-hmm.
We're going to cause it to bump, and then I'm going to show you some things about the machine that are different. And so what you want to pay close attention to is when we start the machine, you can see here that here's our output current, right?
Okay.
And our battery, and this is our input current.
Okay.
See? But so what you're seeing here, this is the energy going to the output battery. So
Right.
what's it doing? Climbing.
Yeah. And this is speeded up.
Yes. And notice this is starting to climb.
Yeah.
So what we want is we're at about 1.2 amps there, and we're about 2.1 amps there right now because the batteries are pretty much charged from us running the machine. So all you need to do is take this current, divide it into that current, and the machine's at about 2 to 1 right now. Now as these batteries start to climb more and more, they're going to boil off. So the machine is made to taper the charge so that the charge goes up high when these are down low. A lot of
Just
current.
like the pendulum did?
Yes.
The lower thing, the
Yes.
speedy thing was
Yeah.
there.
And so if we let it go for a little while, you can see what's going to happen. It's just going to start climbing up. You can see on this meter that when it's in the down position, this is your recovery mode, you're already way into the
Yeah.
charge range.
Yeah.
And this one is C-stable,
Right.
pretty much.
Yeah.
This indicates now that the machine is on because the position of the switch.
Okay.
So if we turn that off, we don't burn any energy. We get everything out of the coils. And what's going to happen is it's going to accelerate to, I think, about 18 RPM here. Looks like about 17 or 18. And that white dot that you see there, right?
I was wondering about
You
that.
asked about, that's a timing. That's for timing.
Okay.
So if you set this, let's just say we didn't have an RPM gauge, right? So we'd set that to 1 minute, right? And we wait for that dot to come around, and bang, now count them. And that'll tell you how many RPMs
Okay,
it's
yeah.
doing in 1 minute, all right? So I think it's what, at 2, 3 now?
I think that's 4.
Yeah, 4. Okay, 5, 6,
7,
7,
8, 9, 10, 11, 12, 13, 14, 15, 16, 17.
17.5.
Yeah, okay.
So it's doing 17 and a half RPMs in a minute with a lot of torque. Because remember what I said, you've got this lever way out here at 6 feet,
Right.
and there's tremendous torque there right now because you've rotated this 300 to 400 pound mass up to that many RPMs. So look at the surface speed if you watch it go around.
It's pretty quick.
Yeah,
If you look at that, it hardly moves, but
right.
yeah.
So if we tell it, see how we're tapering off on charge? Now we're starting to really taper off.
Yeah. Oh, it's going to
See?
39 then.
Yeah. Yeah. Yeah, you can see.
38.4.
Yeah.
So yeah.
Yeah, it's charging pretty quick with this current. So pretty soon it'll be at 40, and then be at 41, and then pretty soon it'll be at 43. And these batteries are boiling at 14.8 volts or 14.5 volts. Your car doesn't like to take your car battery over 14 volts because you'll boil it away. So the real question is how much charge is in those batteries, right? Well, that's why we sucked 200 amps out of them in the beginning
Okay.
with this. So for the appropriate amount of time, we sucked 200 amps out of this one, 200 out of this one, 200 out of this one. So what we could do is if we want the energy and we want to recycle this energy, right? All we need is standard inverter here and a power supply here, and then just send it back here and do it perfectly.
Yeah, okay. Just like your old motors. The original
Yes.
ones, yeah.
But with much more efficiency.
Right.
And that's what we want to have happen with this. Now, if we make this capacitor bank here bigger, right? Then the current will increase here. So right now, I wanted to have, when I first started this morning with it, when you guys came in and it was running, it was doing, 5 to 7 amp pulses. Then we went to dinner, shut the machine off. We came back, the batteries kept charging.
Yeah.
This is exactly what Tom Bearden's talking about when you do this kind of time charge on the battery. So that's basically an explanation of the machine and what the functions of the machine are.
So what's that box there?
This is the controller for that timing wheel on the back to fire the impulses.
Okay.
And all the energy that comes back from these coils, right, is dumped out of here to this capacitor over here. See?
Okay.
So it dumps to this capacitor, and then in this box is a switch that when it sees this charge, this dump, it fires and sends the energy to the battery, as you can see, when you push that switch down. Now,
Yeah.
now look where the meter is, Pat.
Yeah, I know. And this is at 40.7 too.
Yeah. So, you know, why would I worry about charging any batteries? There it is.
Right,
You know, you can see what the efficiency is. We didn't run it very long.
right.
And it's all in this, on tape here. So very little input in spikes and very large output in the phi current. So we were able to meter it. By the way, this is inverted circuits.
What does that mean?
This is what's discussed in 30 years, Beardena and Bedini, right? Inverted circuits, because this is an inverted circuit and it comes in on the negative.
Okay.
And this one comes out on the positive. So it's inverted. And see where it just jumped?
So that, yeah.
The battery is under charge. See? And notice where this battery is. That's the recovery battery. And here's the primary battery. See? We're just now approaching the green. Because we've been using the machine.
Right.
But what's very important is that right there. Is what it's doing to those batteries.
Yeah.
See it? It's bouncing this. It's tapering
You
off.
know what, this is bouncing too.
Sure. And this is the charge battery. See, it's bouncing.
Right.
Inversely proportional to that. So there's your primary again. This is tapering off because this is at 42 volts now. So the batteries aren't requiring any current from the machine.
Okay. Cool.
So basically, Pat, the machine's running wild right now. But servoed, because it's in this magnetic lock. Well, the machine is running wild, basically wants to run, right? Wants to take off and go. But we're limiting it because of this generator now. We're holding the machine under a torque load.
We started at 38.4.
Yeah.
We're rising to 42.8, 0.9, 0.9.
The watch pop little boys.
I know, but I just wanted him to catch that.
Yeah.
It's actually 43 volts. That meter's like 5 off. Because it's slammed here. That's 30. That's almost 45.
43.0.
Yeah. Oh, it's going to go. It's going to go up. Okay, so we're at 43.1. We're at 14.36 right now on each battery.
So they are boiling.
Yes.
John, I have a question, which may not be relevant, but does this relate at all to the motor that Jim Watson built and which he showed at the Tesla Symposium 20-something years ago? I mean, is this...
Yes, except that this would be depicted as Jim Watson's generator,
Right. This part.
and this would be depicted as Jim Watson's aircraft generator. Now, one important thing that I forgot to tell you is Jim Watson didn't have the capability, he may have it now, underground somewhere, but didn't have the capability of being able to do the regauging in the generator. So this is far superior to his machine. and that it's burning no current, and he had to use a jet aircraft starter to get that big mask on. But all we have to do is flip a switch and change the magnetic fields, and the mass starts rotating and starts outputting to recharge the batteries. And like we filmed earlier on, you can just, it's already at 40 volts. And so it's pushing those batteries up there. But the thing that it is doing, Tony, is it's conditioning these batteries with a time charge. So if you measure these batteries and you measure these batteries don't have this sustaining power of these. So we don't have to depend on a great big gigantic flywheel. We're actually pushing the flywheel with magnetic streams
Right.
around here. So we shape the magnetic field by shaping it, by bending this iron, right?
Right.
And so what we want to do is we want to ride the magnetic stream.
How many magnetic streams are there? I mean,
There's 16,
yeah.
you know, and depicted, I think, in the Coral Castle stuff, there's 16 more magnetic streams.
The Carl Ed Dean scans.
Yeah.
Carl Castle.
Yeah, he said ring the bell twice.
What does that mean?
Drop through the zero.
Zero potential.
Yeah, drop through the zero potential and there's the energy.
Oh yeah.
See what I'm saying?
Yeah.
So that's exactly what we're doing. And that's exactly what Tom Beardena was saying, is the phi, right,
Right.
current is a zero current,
Yeah.
massless. It's magnetic. It's magnetricity is what it is. It's all magnetism. So,
So these 16 streams, wasn't that also in the Sumerian tablets? Or was
yeah, it was in the Sumerian text. It was Masonic temples.
Yeah.
It's always depicted with the star with 16 major streams. I think, you know, there's quite a few people on the internet that made us the 144 code. The numbers come out right.
One
And nobody has gathered this kind of energy with it.
Right. 144 code's the website.
Yeah. And the guy's right.
Right.
It's just he hasn't got the energy.
So this is the timing plate on the back of the...
Right. This is the timing wheel on the back of the machine. You're facing the front when we're looking at it in this video, but this is on the back, and you can see that there are 16, if you count them, 16 magnetic poles, all south. The disc sort of looks like this, but it has 16 poles. So these are identical, with the exception that this one has to be big because you need to get the 16 1-inch round magnets all the way around this. And that's running the Hall device on the back. There's a little Hall device that's in the back, and we'll show it in another picture. So yes, that is your timing device. And over here, it's kind of hard to see, but you can see there's sort of a red cast here. See it right there? Right in here.
Right.
Those are marked off with a protractor in degrees. So the magnet is set to be, when it fires this motor, at exactly 23 degrees past.
Okay, John, now, can you go through what's going on here?
Okay. This here is a Radis motor. This works identically to what the astronauts' shoes that's depicted on Tom Bearden's internet site.
This is Raymond Radis that used to work.
Yes, Raymond Radis.
Used to work for NASA.
Right. So, to make this motor work, it requires that you need a magnet with a memory. So that's a barium ferrite magnet. And so we'll go back and I'll show you the disc for that. So we're going to come up on this a little bit. Okay, a little bit better view.
Yeah, yeah.
On the back here, right in here, these poles, there's a hole drilled through the wood because there's a diamagnetic material, which is the wood, and then there's a magnetic material behind it. So this is a steel plate, 1/8-inch steel plate, that is filling the entire space of this piece of wood with a 2-inch hole cut here. Now, notice here, right here, you see this circle? That fits the exact spacing so that when this magnet spins, it goes through this arc so that it gets the travel of the exact 1 inch on this plate. But used in this one, the one that's in there right now, there's a 1/2-inch magnet because we had too much travel and we couldn't get the shoe to release. It tried to overlap each time and pull backwards. So you have to have the correct spike to switch the barium ferrite magnet into a memory effect, which at that point in time shakes. Because remember, it's almost built like a pancake. Okay, so we've seen the mounting side of the magnetic coils, which are basically being wound around the magnets, but with coils that couple through the iron. So this, again, what you're looking at here is you're looking at the magnets, the shape of the magnets. It's this shape because we only need this much arc. And I had them because I had them cut years ago to make this type of motor. All right, so these are barium ferrite magnets. They've just been painted. I held one of them up for you and showed you that they rust. They're bonded to this metal plate, and this is a metal plate surrounding the whole disc, so that the fields in this metal plate pass from the bottom to the next bottom, to the next bottom, to the next bottom. So they're not going through the metal shield. They're just passing through as if they're straight lines from here to here at this angle. Notice this angle, right, is in a V also, almost like a pyramid shape, right? So you have 10 poles. So you have north and you have south poles. You can see the south symbol here, south symbol here, south symbol. The ones with the dots on the front of the wheel, as depicted in the video, are north poles. You can see there's a north pole here, so there's a north pole here, north, north, north. So instead of letting these magnetic fields ride out in a loop fashion, we make the lines go through the iron straight, but at this angle. Notice the angle. It's a wider V than this V, because we don't want quite the same strength out here that we want in here. So what we're actually doing here is we're causing the magnet to be nonlinear. In this picture, we showed you the top version. All right, once again, we don't want the magnetic fields coming out like this and going around and coming out like this and going around. What we want the magnetic field to do is cross the iron in straight lines. No nonlinearity. So now we have a linear thing and we have a nonlinear thing. And what we're going to do with this is we're going to put a little bitty spike into these coils, and we want the nonlinear portion of the way the magnets are arranged to flip their fields magnetically. Now, we've mounted this disc on the machine. This point, and an adjuster so that we can get the angle to the magnets. And we've angled it off a little bit by this adjuster so that one side of the wheel is a little bit more nonlinear than the other side of the wheel. And you can see that if you get alongside this wheel. This is exactly how the coils are arranged.
Why did you want that non-linearity?
Because I want the magnet to switch itself.
Okay. And about how many degrees of angle do you put on the base plate?
On which plate?
On this plate, you say this is adjusted down like this.
Right.
What,
About
half degree, quarter degree?
No, about 3 degrees.
Oh, that much?
Yeah, 3 degrees, because we want this wave to show up. We want the magnetic material to go around in a non-linear fashion.
Okay.
And it's going to be more like an ocean wave when it goes around. It's going to have a high and a low, and it's going to keep doing that.
Wow.
All right?
Very subtle.
Yeah, very subtle. We want to mix this. Now, what you're seeing right here is this timing plate without the magnets on it. It's facing this direction. All right? So you can see how we've wired these coils. We've taken the two bottoms of these two and put them together, and we've taken the two tops of these two and put them together, and we've taken the two bottoms of these two and put them together, and we've done that all the way around the wheel. Okay, now what we've done after we built our magnetic disc, and because as I said earlier, we want these magnetic fields to be concentrated in one area and not quite as much in the other area. So we want the magnet to be, its magnetic field to be shaped in a non-linear fashion so that it can switch. Here's, in this circle, see the dots? That's where we know there's 10 positions. So we're only going to use 5 of these positions because we only want to cause the nonlinear on the north poles. Because when the magnet flips, when it shakes, and the barium changes, we want the motor force for free, which means 0 current on the meter that you're looking at. And that means that this motor has given it a little trigger signal to flip the magnet, and we want this to be sucked in because we want it in attraction. That's free for the taking when you're in attraction. When you're in repulsion, it costs you energy.
Yeah.
We want it to be sucked in to this nonlinear field. And then we want the magnet to flip back the other direction. And we want to add that pulse again, so that's why we've done north-south poles, or we would have done all north poles.
Yeah.
Because it's typical of the type of generators that we do. Now, I'm going to bring up a very important point here. I want everybody to understand. This was my original motor, but See, Jim Watson discovered the arrangement a little bit different. And how you can tell that he discovered the arrangement a little bit different is, see, these aren't in line with the magnets, they're advancing. So he's creating that nonlinear field. Those are barium ferrite ring speaker magnets. So we're getting this switching effect automatically in these poles. Except Jim Watson forgot one thing, that should have been metal underneath here and metal on the back where the poles came through. So therefore he can't take advantage of getting any advancement for free. So therefore he has to supply current to keep it advancing. Where we're not supplying current, we're asking the magnetic field itself to give us the current for free. So I want to point out that even though the two machines, this is depicted as something which is the original Bedini type converter built. That is the Bedini type converter in what I'm showing you. That's the correct way to build it. In this picture, you can see a little more clearly. If you look down here, these marks indicate the 10 positions. And you can see that there's no metal on this side of the coils. Normally, you would put metal on this side. No, because here's something that when you're dealing with this type of energy, or it loves resistance. You get more energy with resistance. So we're actually spacing this further here between here and here with metal to get the resistance, because negative energy manifests itself in resistance. Even Tesla knew that. That's why he built the Tesla coil with many turns to get that voltage as high as he could, to get the negative energy or the radiant energy out of it. Here you see on the mill that this wheel's on the dividing head, and you see all the marks to place those V-shaped magnets. So we've divided it in degrees. You can see here, it's kind of a little bit hard to see, but you can see right down here, I think it says 105 degrees. All these degrees tell us where we're going to place these magnets.
What are these ridges here?
The ridges.
Looks like a hot plate.
Yes. Well, the metal was completely rusted. We rusted the metal completely before we assembled it. So after the metal sat out and rusted and rusted and rusted.
Why did you let it rust?
Well, we let it rust so it wouldn't be conductive. We were doing a different experiment.
Okay.
So what we did was we put it on the rotary table, and we put not this milling cutter but a wire brush
Okay.
in it, and we spun the rotary table around, right, and carved off the rust. You can see the rust in here, but see, it doesn't make any difference because the barium ferrite magnet's going to rust on it anyway.
Right.
So there'll be just a big group of rust underneath that magnet. Now we'll show you something very important. We took the milling cutter and we divided the 10 poles, and so we wanted to know where to place the center of the magnet. So we measured the magnet at the smallest end and at the largest end, and put 2 dots on the magnet, and then we could just place it on this line, and it would be right on line where we wanted it. Okay. This picture is the stages where we're just bonding these coils after we've sealed the back of this right here, this metal, and we've pounded the welding rod. And now what Gary's going to do, who's standing there, is he's going to grind these to the levels that we want on each coil, because we want a nonlinear function. We want to bring some of them down, and we want to bring some of them up. When you're dealing with something that's re-gauging, you have to be nonlinear, or it's not going to re-gauge. You have to create an imbalance in the magnetic field. So these are different heights.
Every one would be a different height.
Yes, they wouldn't correspond. See, remember,
Right.
we're in a tilt by so many degrees.
Right.
Notice these back here.
Yeah.
It was done on purpose, everybody.
So just a question. These are the low ones here?
Yes.
Would that be the high end of the tilt? Or the
Yes,
low
that's the high end of the tilt.
end? Right,
We're going to tilt it,
Yeah.
and these are going to move away.
right,
We're going to concentrate more energy
right,
on these when we tilt in,
right.
and these are going to have less energy.
Yeah.
So we're causing an imbalance in it. Okay, and notice we have not hidden the turns from you. There are 2,206 turns of number 18 wire there. Okay, and what we're going to do after that is we're going to connect these two wires, this one on this bottom and this one on this bottom, together, and then we're going to connect this top and this top together, and this bottom and this bottom together, and this top and this top together, and we're going to do that all the way around. So it's like a merry-go-round in a way,
Yeah.
because we want to send the electricity. We want to send the little spike. We want the spike to flip around back and forth, because we know we're going to get a difference
Yeah.
in potential in each spike because of the way we're going to arc the wheel and the way we ground the poles. Okay, going back to this portion of the wheel, you'll notice that what I did was I took aluminum and boxed these in after we bound the magnets up. Because when you get a mass that's this heavy, these are 1 inch thick and probably weigh a pound each or 2 pounds each. What we did was we took straight metal and put it in the press, and we bonded the aluminum, and then screwed it to hold this in a V-cup, so that the force coming outward, it can't come through the V.
Right.
Okay. Anyway, this is me cutting welding rod and shoving it down through this core. Now this core was a little bit tricky because if you see this ridge right here on this bobbin, you had to cut wires that are inset in between these two ridges. So you had to put them in first because they're not quite as long as these. So you had to fill the full space of the coil. And then of course after these are forced in that space, they're bonded in, they're glued in. And they're glued in the bottom where the coil's inset into the wood.
Which particular coil is that?
That's the biggest coil.
In the center?
Yeah, you can see it's the biggest coil because you have this plastic here.
Right.
And you can see the metal shield's already on.
Right.
It's already bonded, and you can see that it's not tuned yet
Right.
because it's not spread out.
Right.
Okay? In this position in tuning, the magnetic field's going to jump. It's not going to swing. It's going to try to just curve over like this. Okay, and when you bend these down, the magnetic field's going to swing out bigger, because what we want to do is we want to force the zero out of the center. We want a neutral point real big in the center, so that there's no conduction when the magnet comes across, because we're going to use the impulse technology that we talked all along about to pulses. Okay, as I said, this is exactly what's inside the machine, and these are the hookup wires to the rectifiers. for the back pulse. That captures it, right?
Right.
And that goes back down to that capacitor that you see in the machine. And this is the input to it where the power is going to come in.
Right.
So that's going to be tied right here, and then the wires are going to come out here and come through a hole, which you can see in the machine. And that's the switch. That's the Bedini coil switch that's going to generate this little bitty spike to switch these. And that's the number of turns. 2,206 turns of number 18 wire, every one. That's a pretty good one because you can see we're hooking up the wires.
Right.
Okay, in this picture, you can see that we're hooking up generator wire coming out of here and input wire to get the little impulse spike.
Right.
And that's going to be triggered by this device, which is already hooked into the switch in this red and white and black wire that's coming around here and ending up at the hull. Okay. In this picture here, David Luke is machining another one of these timing plates for smaller magnets because we found that using these bigger magnets that we overlap the fields that we wanted to have work for us. Better picture of it. Here's a little bit better picture of it being very close to finished. So anyway, Pat, this was for Tom Bearden.
Mm-hmm.
Happy birthday, Tom.
Yeah.
And here's your machine.
I'm sure this is the best birthday present he could get, probably.
Hope so.
Yeah,
Because
it
it's-
validates all his years of work.
Yes, it's right there in front of everybody.
Right.
It's metered. Nobody touches anything. You can look at all the wires. Everything's on the top exposed. You can watch the battery. By the way, this is at 43.8 right now.
Yeah.
So it's almost at 44 volts, which is,
That's skipped up 6 volts.
yes, just like that.
Yeah.
And that is what I want to tell everybody is energy from the vacuum if you do this right.
Yeah.
So,
Yeah, it definitely vindicates
yeah,
old Tom's,
it vindicates
validates
his
all
life's
big
work
words. Yeah.
in free energy, or what he terms free energy. It isn't free
Right.
in the term that, because it costs to do all this.
Right.
So,
But you're not on a meter.
but I'm not, right, I'm not on a
You're
meter,
not an
and I'm not burning gobs amount of fuel
Yeah.
to turn this mass. See, right now, this could be pumping water for me.
Yeah. Yeah.
So in the end, Pat, whether it's aluminum, wood, whatever, cardboard, if that's all you had, it would do the same thing.
Yeah. 44.
Yeah. So happy birthday, Tom. You can see them, they're half-inch buttons.
Oh, okay.
They go across the switch, and see these dots? Here.
Okay. Yeah.
That's on the north pole.
Yeah.
Okay, so when a dot comes across this pole, it switches on. And when the coil collapses in the re-gauge mode between the metal, it sucks it into the next thing, which adds the torque.
So this is sucking it around. Right?
Yes, yeah, in their pie shape, see them?
So that's the radish thing.
Yes.
Yes, that's the radish thing. Yeah.
Yeah, that's a Radis motor.
Yeah. That's the radish motor right there.
Right there, that's a Radis
So
re-gauging
you have
motor.
about 8 different motors running in one.
Yeah, you have to put them all together. You have to put the whole theory together.